Hello everyone, I am Prabhat Kumar Neria. In this video, I will be discussing about the laser Doppler anemometer. Okay, so it is a non-intrusive optical technique which used to measure the fluid velocity with very high accuracy and very high resolution. So it is based on the Doppler effect. So what is the Doppler effect? It is the change in the frequency or wavelength of the wave observed by an observer when the source of the wave and the observer are moving relative to each other. So here we can see their particles should also have the velocity and fluid some have some also velocity. So because of their relative velocity, there may have a relative frequency. So in this, I will be talking about introduction, its working principle, its components, its applications, and some future perspectives. So it is based on the non-intrusive measurements, which means uh, it measures the velocity without affecting the physical property of the sample, or can say without creating any disturbances in the uh, flow field. So which is very crucial for the accurate analysis, particularly for the particularly for the complex research. And it gives high spatial resolution. So it gives only the velocity of only that particular location, that specific location, whatever you want. So because of that, it is again very valuable for studying the complex fluid dynamic. And it has versatile applications that may be the Doppler radar, or can say non-destructive testing, or can say laser scanning. So because of these versatility, uh, it becomes very powerful tool for investigating the fluid flow. And fourth, it gives the accurate velocity measurement. So our researchers can reliable on the on its data and analysis for the further applications. So the working principle. So it has generally uh, four components. One is the laser beam, second is the scattering particle, Doppler shift, and frequency analysis. So the laser beams are coming from the laser and which go into the transmitting or can say receiving optics. And the transmitting and receiving optics have the lens in which the beams are going into that, and at this point they will be intersecting. So at that intersection there will be creation of fringes because of the interference. So there are flow with the seeding particles. So these particles will be seeded to the flow and acting as a scattering centers. So these will be interact with the fringe patterns of the scattering lines, and because of that there will be the shift in the frequency which is called Doppler shift frequency. Uh, so which is directly proportional to the particle velocity, and from here we will get the our frequency uh, from the signal processing. So this is our signal processing, and it can be in the time series, or it can be in the another form as well. So optical setup. So mhm, here are basically three components. One is the laser source, second is the optical components, and third is the photo detector. So this is the laser source in which high power laser coherent light provides, which is necessary for interference pattern, and which is generally of infrared spectrum or visible as well. And this is the optical component. So it is having a lens beam splitter. So this will split the beam into two parts, and this is the lens, and this lens will be converging the light into that location. So this is our flow with the particles. So what does these lenses and beams do? These ensure the precise alignment and optical beam intersection. And third is our photodetector, which detects the signal and converts the light into electrical signal for further analysis. And calibration procedure. So the calibrating the laser Doppler anemometer is very critical. So to ensure our result should be accurate, so we should have some key steps. Uh, that is initial setup and alignment, velocity references, and environmental control. So to ensure the optical component should be properly aligned, and we have to also ensure that spacing between the laser and inference fringes. And second is the velocity reference. So we use a rotating disc or linear motion stage with a known speed to the calibrated and or laser Doppler anemometers velocity. And third is the environmental control. So to maintain our system should be stable, like pressure, temperature, and our vibration condition should be stable, so that measurement should be accurate and should be reliable. So we have to be minimize our measurement errors from these control. Okay, so we will be having a three components in the Doppler shift and velocity calculation. So first is again Doppler shift. So the frequency shift experienced by the scatter light, which is directly proportional to the velocity, and the fringe spacing, which is lambda by 2 sin theta. So here the lambda is the wavelength of the laser light, and theta is the angle between the intersecting beams. So from this, our velocity will be frequency shift into lambda by 2 sin theta. Okay, there may have some advantages of laser Doppler. So uh, this is again non-intrusive, means it doesn't require any physical probes or sensor to be inserted into the flow. So minimizing the disturbances and ensuring accurate measurement. And it have very high accuracy. So it provides very precise velocity measurement. So we can rely on its data and its analysis for our other applications. And it has high temporal resolution, which means it can capture velocity fluctuation in real time and providing insight into the dynamic behavior of the fluid flow. And it will having also the versatile applications, which means it is adaptable to a wide range of flow conditions, including very high speed flows, or can say turbulent flows, or can say multi-phase flows. Okay, so application. So here are some application as well, which are like in the aerodynamic, turbine performance, flow visualization, and combustion research. So in the aerodynamics, it is used in a wind tunnel for testing to analyze the airflow patterns around the aircraft, and it provides the valuable data for optimizing the aerodynamic design to reducing the drag. In the turbine performance, it helps to as assess the efficiency, or can say helps to increase the performance of the turbine, such as wind turbine, gas turbine, and it provides the very detailed information about their characteristics. And flow visualization. So it visualizes the complex flow patterns such as vortices, boundary layers, wakes, and this visualization is very crucial for understanding the behavior of fluid flows in various applications. And combustion research. So in this, it provides the research to study the flow of mixing of fuel and air within the combustion chambers and improvement the engine's efficiency. And seeding particle and considerations. So in our laser Doppler anemometry measurement, we have to be think about the seeding particles. Like there are some three key steps. One is the particle size, second is the particle concentration, and third is the particle refractive index. So our particle size should be significantly smaller than the smallest. So that This ensures the fluid velocity should be accurately measured. And particle concentration. So the particle concentration should be sufficient for good signal to noise ratio, but not so high because it can alter the flow characteristic. And particle refractive index. The particle refractive index should be different from the surrounding fluid to maximize light scattering and ensures accurate velocity measurement. It has some limitations and challenges. Uh, it is although very powerful, but it has some also limitations. So there may be optical axis, particle shading, signal to noise ratio, and ambiguity resolution. So the flow region must be optically accessible for the laser beams to pass through. And particle seeding. Here seeding particles can alter the flow characteristics, especially at high concentration. And signal to noise ratio. So low particle concentration or background noise can affect the accuracy of velocity. And again here we can see the Doppler shift can be ambiguous, requiring additional techniques to resolve the direction of the movement. Some emerging trends and future developments. So it is continuously evolving with advancements in technology. So there are some key steps: miniaturization, high-speed measurements, multi-component velocity measurements, integration with other techniques. So it developed the compact, you can say, combined spaces and portable applications in the miniaturization, and improvement in the data acquisition and processing techniques for measuring high speed flows. So, and again, the development of techniques to simultaneously measure multiple velocity components, like instead of measuring in only one direction, it can measure the velocity in all the directions, like x, y, and z. And integration with other techniques, like combining this LD system um, can the particle image velocimetry and other uh, techniques for comprehensive flow analysis. Thank you.